There is no center of the universe, or rather, every point in the universe is the center. Right now, wherever you are lying down, you occupy the exact geometric middle of your own observable cosmos. The stars curve away from you in every direction at equal distances. The galaxies thin out toward a boundary you can never cross, never touch, never even define in any physical sense. And that boundary is not a wall. It is not made of matter or force or anything at all. It is simply the farthest distance that light, traveling at the only speed the universe permits, has been able to reach since the beginning of time. 13.8 billion years ago, the universe began.
That is the only number we have for when time itself started. Not just when matter began or when space began, but when the very concept of before became meaningless. Everything that has ever happened, every event in the history of the cosmos, every chemical reaction, every star ignited, every galaxy assembled from the wreckage of smaller structures, all of it fits inside 13.8 billion years. That is your budget. That is the only currency in which the observable universe was purchased. And because light takes time to travel, we can only ever see as far as light has managed to come. Every photon that reaches your eye tonight has been traveling, some of them for nearly the entire age of the cosmos.
They left their source before the Earth existed, before the sun had condensed from a cloud of gas and dust, before most of the stars you can see had been born from the ashes of older, heavier stars that lived and died before them. The light is ancient. It has been in transit for longer than the planet you are lying on has existed, and it is still arriving. But here is where the geometry becomes strange. The universe, during all that time, has not been sitting still. It has been expanding. Not expanding into something, not growing into a larger space that contains it, like a balloon inflating inside a room. Space itself has been stretching.
The fabric of the cosmos has been pulling apart at every point simultaneously, carrying galaxies away from each other the way raisins in a rising loaf of bread are carried apart. Not because the raisins are moving through the bread, but because the bread itself is growing in every direction at once. What this means for the light traveling toward you is this. A photon emitted 13.8 billion years ago from a source that was then perhaps a few 100 million light years away, has been traveling through space that was expanding the entire time it traveled. The source of the photon is now much farther away than it was when the photon left.
The photon crossed the early small universe, and by the time it reaches you, the source has been carried billions of light years further by the expansion of space. The result is a number that sounds impossible. The observable universe is not 13.8 billion light years in radius, the figure you might expect if light had simply traveled outward at the speed of light for 13.8 billion years. It is 46.5 billion light years in radius, 93 billion light years from one side to the other. That is the diameter of everything you could, even in principle, ever see. The expansion of space has stretched the observable universe to almost 3.5 times the distance light alone could have covered.
Think carefully about what this means. The most distant things we can observe are not where they were when they sent us their light. They have been carried away by the growth of space, and they are now receding from us. And some of them are receding from us faster than light. Not because they are moving through space, but because space between us and them is growing at a rate that accumulates over those vast distances to a recession velocity exceeding 300,000 kilometers per second. And this does not violate anything. Einstein's relativity forbids objects from moving through space faster than light. It places no restriction whatsoever on how fast space itself can grow. Think about what it means to live inside a sphere like this.
A bubble of knowable reality, centered on you, defined not by what exists out there, but by what the speed of light has had time to deliver. Beyond the edge of that bubble, the universe continues. It almost certainly continues, but no photon from that darkness has yet had time to reach you. And some of those photons, given the acceleration of the expansion, will never arrive. They are already falling behind, already losing ground against an expansion that grows stronger the larger the universe becomes. And the boundary of your observable universe moves with you. It is not fixed in space. It is centered on you, on your position, your reference frame, your moment in time.
If you could somehow move to a galaxy 1 billion light years away, you would be at the center of a new observable universe, overlapping with this one, but extending further in the direction you traveled. Every observer in the universe has their own observable sphere. No two are quite the same. Each is a prison made of light and time, and each is entirely personal. Now reach further back. The oldest light we can detect is not from stars or galaxies at all. It predates both.
In the first few 100,000 years after the beginning, the universe was so hot and so dense that light could not travel freely. Every photon was immediately absorbed and re-emitted, trapped in a fog of charged plasma that filled all of space, bouncing between electrons and protons like sound trapped inside a solid wall. The universe was opaque. Light existed, but it could not go anywhere. It was imprisoned in matter. Then, at around 380,000 years after the beginning, the universe cooled just enough, to around 3,000 degrees, which sounds hot but is cold compared to what came before. At that temperature, electrons could combine with protons and form neutral hydrogen atoms. The fog cleared. The plasma became transparent. And light streamed outward in every direction for the first time in the history of the universe, free at last, carrying with it the thermal signature of that brief moment of clarity. We still receive that light today. It has been traveling for 13.8 billion years, and the expansion of space has stretched it so severely that what was once 3,000 degrees of infrared and visible radiation has been redshifted into microwave frequencies. Wavelengths measured in centimeters rather than fractions of a micron. It arrives cold, barely 2.7 degrees above absolute zero, a whisper of thermal energy that fills the sky in every direction with perfect uniformity. We call it the cosmic microwave background. It is the wallpaper of the observable universe. The last surface, the farthest we can see. When you look at the cosmic microwave background, when you point an instrument at the sky and collect that ancient radiation, you are not looking at empty space. You are looking at the surface of the particle horizon, the actual edge of everything that has ever communicated with us. Beyond that glowing shell of ancient light, there is more universe, but it existed before light could travel freely, and the signal from it, the gravitational imprint, the tiny fluctuations in density that seeded every galaxy that would come after,
is encoded in the patterns of the background radiation itself. The earliest moments of the universe are not invisible.
They are written in a language we are only beginning to read, but the universe beyond the background, beyond the horizon, beyond the edge of what any instrument can reach, that is a different matter. That is not hidden behind a technical limitation, it is hidden behind a structural feature of reality itself. The horizon is not a wall that better telescopes will someday penetrate. It is the causal edge of our universe, and it is as final as anything in physics has ever been. You are standing at the center of a prison made of light and time. The walls are not solid. They are the limit of what has been possible, given the age of the universe and the speed of its one universal constant.
And they move with you. Wherever you go, you remain the center of your own observable sphere. There is no escaping to a better vantage point. There is no hilltop from which more of the cosmos becomes visible. You take your horizon with you, always. It is yours, and only yours, and it defines everything you will ever know.
Most people, when they think of the edge of the universe, imagine one thing: a single line, a final boundary, a wall beyond which everything stops. The universe offers something more precise and more unsettling than that. There are three distinct horizons, each defined by a different principle, each marking a different kind of limit, and each one is a different form of forever.
The first is called the Hubble radius, named for Edwin Hubble, the American astronomer, who in the 1920s demonstrated that the fuzzy patches of light scattered across the sky that other astronomers had called nebulae were in fact entire galaxies, systems of hundreds of billions of stars so far away that their individual stars blurred together into a single smear of pale glow. Hubble also measured something stranger. He found that almost all of these galaxies were moving away from us, and that the farther away a galaxy was, the faster it was receding. Not because they were fleeing from some explosion centered on our location,
but because space itself was expanding, and the more space there was between us and a galaxy, the more expansion was accumulated along that distance, producing a higher apparent recession velocity. The Hubble constant, the rate of that expansion, means that at a specific distance, roughly 14 billion light-years from where you are lying right now, galaxies are receding from us at exactly the speed of light, not moving through space at the speed of light. The space between us and them is growing at the speed of light. The Hubble radius is the distance at which the recession velocity, due to expansion, equals light speed. Beyond the Hubble radius, galaxies recede faster than light. This is already true of most of what we can observe.
The galaxies visible in the deep field images taken by the Hubble Space Telescope, the faint smears of light at redshifts of 2 and 3 and 6 and beyond. All of them are currently receding from us faster than light. We can see them. Their light reached us long ago. But if they emitted a photon right now in this moment, that photon would be born into space that is already carrying it away from us faster than it can travel. But the Hubble radius is not the boundary of the observable universe. And here the geometry becomes remarkable. Light that was emitted beyond the Hubble radius can still reach us.
A photon born 14 billion light-years away in a region where space is currently receding at the speed of light, can still make progress toward us, not because it is faster than the expansion, but because it is moving through space that is not uniformly expanding at that rate at every point along its journey. The photon travels through regions where the expansion is slower, where it can gain ground. If it is aimed in our direction, and if it was emitted early enough when the distances were smaller, it can traverse all of that expanding space and still arrive. This is why the observable universe extends to 46.5 billion light-years, well beyond the 14 billion light-year Hubble radius.
We can observe things that are currently receding from us faster than light. We are seeing light they emitted long ago, when they were closer, when the expansion had not yet carried them so far. The observable universe is larger than the region of space currently receding at the speed of light. The particle horizon and the Hubble radius are different things, separated by 32.5 billion light-years. The second horizon is the particle horizon. This is the boundary that defines the observable universe, the sphere 46.5 billion light-years in radius. The particle horizon marks the edge of our causal past.
Everything within the particle horizon has, at some point in the history of the universe, been able to send a signal that reached us. A photon emitted from a location inside the particle horizon has made it across the expanding space and arrived at our telescopes, or at our eyes, or at the simple fact of our existence. We have been touched by it. Everything beyond the particle horizon has never sent a signal that reached us. Not once, in 13.8 billion years. Not a photon, not a gravitational ripple, not a neutrino. Whatever exists beyond the particle horizon is, in the strictest physical sense, not part of our universe's history. It has never influenced anything here. It has never been influenced by anything here.
The causal connection that links every event in our universe to every other event through chains of cause and effect, that connection breaks completely at the particle horizon. Beyond it, there is no causal thread that leads back to here. When you look at the night sky, every photon that enters your eye was emitted by something within the particle horizon. Every galaxy, every quasar, every faint smear of blue shifted starlight, all of it comes from within that sphere. It is the totality of everything that has ever communicated with us, everything that has ever sent us any signal, everything that has shaped the physical conditions in which we exist. It is finite, bounded,
and surrounded by a darkness from which no message has come, and from which no message ever will come. Not in all the time that will ever exist. The third horizon is the event horizon. And the event horizon is where the geometry of the future becomes irreversible. Unlike the particle horizon, which describes what has been in our causal past, the event horizon describes what will be in our causal future. It is the boundary beyond which, for any event happening now or in the future, no signal will ever reach us.
Even if a galaxy on the far side of the cosmic event horizon were to detonate in the most catastrophic explosion imaginable, right now, in this second, the light from that explosion would never arrive. The expansion of space would carry it away, faster than it could travel toward us, forever.
The cosmic event horizon sits at approximately 16 billion light years from where you are, closer than the particle horizon, closer than the edge of what we can currently observe, and shrinking in terms of what it encompasses as the acceleration of the expansion continues. Because while we can see things that sent their light to us long ago, when the universe was younger and distances were smaller, the future is more restricted.
The universe is accelerating. Every year, more of what is currently observable crosses the event horizon and becomes permanently unreachable. This means we are in a peculiar position. We can currently detect galaxies that we will never be able to detect again. Galaxies that sent us their light billions of years ago, when the universe was compact enough for that light to reach us, but which have since been carried beyond the point from which any future signal can return. Those galaxies exist in a region of our current view that is already sealed off from our future. We see their ancient light. We cannot see their present. And we never will. 3 horizons, 3 different kinds of forever.
The Hubble radius is the present. The distance at which space currently expands at light speed, the nearest edge of the region where expansion outpaces light. The particle horizon is the past, the farthest reach of everything that has ever touched us, every signal ever delivered. The event horizon is the future, the boundary beyond which nothing will ever be delivered to us again, not in any conceivable future, not for the rest of time. We live inside all 3 simultaneously. They define different aspects of our cosmic isolation, our separation from the present moment beyond a certain distance, from the entire causal history of most of the universe, and from all the events that will ever happen beyond our reach.
The universe has not given us one edge. It has given us 3, and each one is a different form of the same fundamental truth, that we are not connected to the whole. We are connected to a part, and the part is all we will ever have.
In 1998, 2 independent teams of astronomers were making a measurement they expected to confirm what cosmologists had long assumed. They were measuring the brightness of type Ia supernovae, stellar explosions in which a white dwarf star accretes matter from a companion until it exceeds a critical mass, triggering a thermonuclear detonation that briefly outshines its entire host galaxy. Because these explosions arise from such a predictable physical trigger, they reach roughly the same peak luminosity every time. That consistency makes them useful. If you know how bright something actually is, and you measure how bright it appears, you can calculate the distance. The teams were measuring how far away these supernovae were, and comparing those distances to the recession velocities of the galaxies that hosted them.
The goal was to measure deceleration, to quantify how much the mutual gravity of all the matter in the universe was slowing the expansion. Everyone expected the expansion to be slowing down. That is what gravity does. That is what the equations predicted. The supernovae were dimmer than they should have been. Dimmer, not brighter. They were farther away than the models predicted. which meant
Something was opposing gravity across the largest scales of the cosmos, growing stronger as space grew larger, pushing the universe apart with an energy that had no known source, no known mechanism, no known particle. Saul Perlmutter led one of the teams. Brian Schmidt and Adam Rose led the other. They had arrived at the same result independently. They published. The community was skeptical, then cautious, then convinced as more data came in from different instruments and different methods. In 2011, all three received the Nobel Prize in Physics. The discovery they were awarded for is the accelerating expansion of the universe, driven by what has since been called dark energy. Dark energy constitutes roughly 68% of the total energy content of the universe.
We cannot detect it directly. We cannot produce it in a laboratory. We cannot identify the particle that carries it, if there is one. The best candidate is what Einstein called the cosmological constant, a term he added to his equations and then later removed, calling it his greatest blunder, and which now appears to describe something real after all, an intrinsic energy density of empty space, constant everywhere in the cosmos, exerting a pressure that drives expansion. But even this explanation is deeply unsatisfying, because the value of the cosmological constant predicted by quantum field theory differs from the observed value by a factor of 10 to the power of 120.
That discrepancy is the largest known disagreement between theory and observation in the history of science. What dark energy means for the light that travels through the universe is this: some of that light will never arrive. Right now, at this moment, there are galaxies we can observe. Galaxies within the particle horizon, galaxies from which we have already received light, that are receding from us faster than the speed of light. We have discussed why this does not prevent us from seeing them. The light we are receiving left them long ago, when they were closer. But the light they are emitting right now, tonight, as their stars burn and their gas clouds collapse into new stellar nurseries, that light is already lost to us.
It leaves those galaxies and travels toward us through expanding space. It moves at 300,000 kilometers per second, which is all any photon can do. But the distance between us and its source is growing faster than the photon can close it. Every second, the photon gains 300,000 kilometers toward us. Every second, the expansion of space adds more than 300,000 kilometers to the distance. The gap grows. The photon makes no net progress. It will travel for the rest of time, and it will never close the distance. Eventually, that photon will be stretched by the expansion to wavelengths so long they carry almost no energy.
It will become a radio wave, then a wave so long it carries less energy than is contained in any physical measurement. It will approach absolute zero of frequency. In any meaningful sense, it will become indistinguishable from nothing. Not because it vanished, but because it was diluted by the very expansion of the universe into a signal too faint to ever be received. There is a concept that sits uncomfortably at the edge of this understanding. We are, right now, receiving some light that is the last light we will ever receive from certain galaxies. The photons entering our instruments from some of the most distant visible galaxies are the final installment. The last batch of light those galaxies will ever successfully deliver to us.
After this, their light will be emitted into a universe where the space between us and them is already growing too fast for any further photons to make the crossing. They will keep shining. Their stars will burn for billions of years after we lose the ability to detect them. But their light will fail to reach us. It will scatter into the expanding void between us, endlessly stretched, endlessly diluted. We do not know which galaxies these are. We cannot calculate exactly which photons we receive today are the last ones from a given source. But the physics is unambiguous. At the current rate of expansion, the observable universe will not grow. It will, in an important sense, contract, not physically, but informationally.
The number of galaxies with which we can exchange signals will decrease over time. The universe will become more isolated, not less. Each era of cosmic time will see fewer connections, fewer threads of light arriving from a smaller set of sources. Somewhere out there, a galaxy is currently emitting its last photons that will ever reach us. Its stars are burning. Its gas clouds are lit from within. It is, by every measure, alive. And we are watching it for the last time, without knowing it. The photons arriving now are the goodbye. The universe does not announce these separations. It simply lets the last light arrive, quietly, and then falls silent in that direction forever. Some stars, some galaxies, we are seeing for the last time right now.
And we will never know which ones.
Within the observable universe, within that sphere 46.5 billion light-years in radius, centered on where you are lying, the inventory of galaxies is a number that defies any intuitive grasp. For decades, the standard estimate was 200 billion. 200 billion galaxies, each one a gravitational system of billions or hundreds of billions of stars. Each star a nuclear furnace burning for billions of years. Each system of stars possibly hosting planets, possibly hosting chemistry, possibly hosting more. 200 billion galaxies was the canonical number, and it was already too large to hold in the mind without abstraction. Then in 2016, a team led by Christopher Consolis at the University of Nottingham published a revised count.
They used deep field images from the Hubble Space Telescope, combined with mathematical models of galaxy evolution, and estimates for the number of galaxies too small, too faint, and too distant to be individually resolved by any current instrument. They integrated over cosmic time, accounting for the fact that many early galaxies had since merged or faded below detectability. The result, 2 trillion. 2 million galaxies within the observable universe. 10 times the previous estimate. 2 trillion.
But what it means, what it actually implies about the contents of the cosmos, about the sheer accumulation of matter and energy and complexity and time contained within the sphere of the observable universe, is not something human minds can genuinely process. We are built to navigate a world of dozens and hundreds. We can stretch, with effort, to thousands.
millions. With it, ultraviolet light is outside the range of human vision.
Beyond the particle horizon, beyond the edge of the observable universe, the universe continues. How far it continues, no one knows. The honest answer, the answer that any physicist would give if pressed, is that we have no reliable way to determine the size of the full universe. We can only constrain it from below. The best constraints come from the cosmic microwave background. If the universe had a finite size comparable to the observable universe, or even a few times larger, the geometry of space would show up in the patterns of the background radiation. There would be matching features on opposite sides of the sky, the way a room that is smaller than your footsteps creates repeating patterns when you walk in circles.
Measurements from the Planck satellite, the most precise map of the CMB ever made, show no such pattern. The universe is at least a few hundred times larger than the observable universe. The actual lower bound from Planck data puts the radius of the full universe at least 3 orders of magnitude beyond the observable sphere. Some interpretations of cosmic inflation, the theory that the universe underwent an exponential expansion in the first tiny fraction of a second of its existence, suggest that the full universe may be effectively infinite, or so large as to be functionally indistinguishable from infinite on any scale that matters.
If inflation lasted even slightly longer than the minimum required to explain the large-scale homogeneity of the observable universe, the total volume of space produced would be staggering. The observable universe, all 93 billion light-years of it, all 2 trillion galaxies, would be a region so small relative to the full universe that no comparison in everyday experience comes close to capturing it. Some physicists have attempted to put numbers on this. One estimate, based on inflationary models and CMB constraints, puts the ratio of the full universe to the observable universe at something like 10 to the power of 23. That is a number larger than the number of atoms in the observable universe.
If you were to take the observable universe, all 2 trillion galaxies, and treat it as a single point inside the full universe, you would need 10 to the 23rd of those points to fill the whole. The observable universe on that scale is not even a grain of sand. It is smaller than a proton within a grain of sand. But we cannot confirm any of this. We cannot measure it. We cannot test any specific claim about what the universe looks like beyond the particle horizon. By definition, no observation we can make, no telescope, no detector, no instrument of any conceivable kind can receive a signal from beyond the particle horizon. The boundary is not a technological limit, it is a causal limit.
Nothing that has ever existed beyond the particle horizon has ever been in contact with us. Nothing ever will be. This creates a problem for science, or rather, it forces us to confront the edges of what science can do. Science is built on testability. A claim about the world to be scientific must be falsifiable. There must be some possible observation that would prove it wrong. But for the full universe beyond the particle horizon, no such observation exists. We can theorize freely. We can infer from first principles that the laws of nature probably operate the same way beyond the horizon as within it. We can construct elaborate mathematical models of what might be out there, but we cannot test any of them.
We cannot be corrected by reality. The universe, beyond the particle horizon, is immune to our investigation. And beyond the event horizon, the closer boundary, the one that describes not our past, but our future, the situation is more severe. Not only can we not receive any signal from beyond the event horizon, we never will. In all of time, in every future moment this universe will ever contain, no signal from beyond the event horizon will reach us. The causal isolation is not temporary. It is permanent. It is written into the structure of a universe with an accelerating expansion and no mechanism to reverse it. There are answers to questions about what lies beyond the event horizon. Real answers describing real features of a real universe.
Those answers are not hidden. They simply exist in a region of space-time that is, in the most literal sense possible, permanently outside the reach of any causal chain that leads to us. The information exists. It is encoded in the state of regions of the cosmos we will never touch, never see, never influence. It is simply not here. And not here in this context does not mean far away. It means causally disconnected. Disconnected now, and disconnected forever. You are lying somewhere on a small planet. That planet orbits a middle-aged star in the outer arm of a barred spiral galaxy that contains around 250 billion stars.
That galaxy is part of a local group of roughly 50 galaxies, gravitationally bound, small enough that the accelerating expansion of the universe will not pull them apart. Beyond the local group, the other 2 trillion galaxies recede. Some are already beyond the event horizon. More will follow. In 150 billion years or so, most cosmologists estimate that the local group will be all that remains within our event horizon, all that remains of the communicable universe. By that time, the background radiation will have been stretched to wavelengths too faint to detect. The distant galaxies will have vanished below the threshold of any observation.
The evidence for cosmic expansion, for the fact that the universe is larger than the local group, that there are other galaxies, that the cosmos has a history of growth and structure on scales vast beyond imagining, will be gone. Not hidden. Gone. The information will no longer be arriving. We happen to live at a moment when that information is still available, when the expansion has not yet erased the evidence. When we can look out and see 2 trillion galaxies and measure the cosmic microwave background and calculate the Hubble constant and infer the size and age and geometry of the observable universe. We live in a window of time that is, by cosmic standards, brief. A window in which the universe is still legible.
That legibility has limits. The observable universe is bordered by a silence that is not the absence of something, but the presence of an irreversible boundary. Beyond the last photon we can detect, the universe continues. It continues in ways that are almost certainly more elaborate than anything we have imagined, and in ways that may be so unlike anything within our particle horizon that no concept we currently possess would apply. And we will never know. Not because the knowledge is hidden or encoded in some system we have not yet learned to decode, but because the laws of physics make it structurally impossible for that knowledge to reach us. The universe is not withholding anything.
It is simply larger than the causally connected region we inhabit, and the gap between the two will only grow. Beyond the last photon, the universe continues. We just will never know what it looks like. Beyond the last photon, the universe continues. We just will never know what it looks like.
That boundary we have been circling, the edge of what we can see, is not the edge of what exists. It is only the edge of what the light could reach. And beyond it, the universe almost certainly continues. Not for a little while, not for a few more billion light years, but for a distance so vast that the word vast begins to dissolve before it even makes contact with the number. To understand why, we have to go back, all the way back, back to the first fraction of the first second of everything. In 1981, a physicist at the Massachusetts Institute of Technology named Alan Guth proposed something that most of his colleagues initially found difficult to take seriously.
He was trying to solve a problem in cosmology. Several problems, actually. The universe looked too uniform. The same temperature in every direction, to 1 part in 100,000. No matter where astronomers pointed their instruments, the cosmic microwave background, that faint afterglow of the early universe, was the same. But regions on opposite sides of the sky have never been in contact with each other. Light has had no time to carry information between them. So how did they come to agreement? How did opposite ends of the cosmos know to be the same temperature? Guth's answer was inflation. In the first, unimaginably small fraction of a second after the Big Bang, we are talking about 10 to the power of -36 seconds, a sliver of time so thin it has no intuitive meaning. The universe did not expand slowly. It did not unfurl the way a flower opens in the morning light. It erupted. In less time than it takes a photon to cross a single proton, space itself ballooned outward at a rate that makes the speed of light look like standing still. This is called cosmic inflation. And it was not just fast, it was exponential, doubling and doubling again and again in cascading succession until the universe had grown by a factor of at least 10 to the power of 26.
Try to hold that number for a moment. 10 to the power of 26. If you took a single atom, something so small that 1,000,000 of them stacked side by side would barely reach across the width of a human hair, and inflated it by that factor, it would be larger than the entire observable universe is today. The entire 46 billion light-year sphere that we have been describing, all of it, would fit inside a single inflated atom with room to spare. That is what happened to the space we now inhabit. Before inflation, everything we can see was compressed into a region smaller than a subatomic particle.
The uniformity we observe, that suspicious sameness of temperature across the entire sky, is explained by the fact that all those regions were once touching. They were in contact. They had time to equalize. And then, inflation tore them apart, stretching distances so fast that the light could no longer follow. But inflation did not stop at the observable universe. It kept going. The region of space that inflated to produce our observable universe was just one tiny patch of a far larger inflating hole. Think of it like a loaf of bread rising in an oven, except the loaf has no edges. Every part of it expands. The raisins embedded in the dough
drift apart from one another. Each raisin sees its neighbors moving away.
Each raisin is, from its own perspective, the center of an expanding world. But no raisin is the center of the loaf. Our observable universe is one raisin, and the loaf is incomprehensibly larger. The Planck satellite, the most precise measurement we have ever made of the cosmic microwave background, has placed a lower bound on the total size of the universe. Not the observable part, the total universe, the full extent of what inflation produced. The minimum estimate, derived from the flatness and uniformity of the CMB data, is that the total universe is at least 10 to the power of 23 times larger than the part we can observe. Say that slowly. 10 to the power of 23.
Our observable universe, 2 trillion galaxies, 400 billion stars in our galaxy alone, a sphere 46 billion light-years in every direction, is, by this estimate, a smaller fraction of the total cosmos than a single grain of sand is to all the beaches and oceans and deserts on Earth combined. And that is the minimum. That is the floor. There is no known upper bound. This is not poetry. It is not speculation dressed up in scientific language. This is mainstream cosmology, derived from inflation, which is in turn supported by multiple independent lines of observational evidence. The flatness of the universe, the uniformity of the CMB, the pattern of density fluctuations that seeded the formation of galaxies.
Inflation is not proven. No cosmological model is proven in the way a laboratory experiment is proven. But it is among the most successful frameworks we have for explaining what we observe. And what it implies is this: the universe is almost certainly far, far larger than the part we will ever see. We tend to feel small when we look at stars. But looking at stars is nothing. The night sky, all the light we can collect with every telescope ever built, comes from a volume of space that is, relative to what may exist, smaller than a single grain of sand is to the entire visible cosmos. We are smaller, relative to what may be out there, than a single electron is to the observable universe. And all of our science, all of our history, every civilization that has ever risen and fallen, every language ever spoken, and every thought ever thought, all of it happened inside a bubble so infinitesimally small that the rest of what exists would not notice its absence. And yet, we cannot be certain about what fills that larger space. We cannot send a probe beyond our particle horizon. We cannot receive a signal from regions that receded faster than light during inflation. The mathematics tells us the space is there.
But the mathematics cannot tell us whether it is empty or full, uniform or wild, haunted by structures we have no names for. We are left reasoning from what we can see to what we cannot. And what we can see suggests we are not seeing much. There is something strange about living with this knowledge. It does not change anything practical. The stars still rise. The seasons still turn. The details of ordinary life proceed without any visible evidence that they are occurring inside a bubble too small to register on the scale of the real. But knowing it changes something interior, some sense of proportion, some implicit assumption that the world we inhabit is, if not the whole of things, at least a significant portion of them.
Inflation removes that assumption quietly, without drama, without any moment of rupture. The universe is almost certainly vast, beyond any measure we have words for. And we are almost certainly not a significant portion of it. We are just here, in this particular corner, looking out. Consider what it means that we worked this out at all. The evidence for inflation is indirect. We cannot rewind the universe and watch it happen. We cannot observe the inflaton field, the hypothetical quantum field that drove the exponential expansion, because its effects were complete before a single particle of ordinary matter had formed. What we have instead are fingerprints, the flatness of spatial geometry, measured across billions of light years, consistent with what inflation predicts.
The near-perfect uniformity of the CMB, explained by inflation and difficult to explain otherwise, and the pattern of tiny temperature fluctuations in that background, the seeds that grew into galaxies, which matches the spectrum of quantum fluctuations that inflation would have generated when it stretched the universe outward. These are not proof, but they are convergent evidence from independent directions, all pointing to the same conclusion. Something like inflation almost certainly happened. And if it happened, the universe is vastly larger than what we can see. And if the universe is vastly larger, then everything we have spent the last century learning to understand is a local description of a tiny region, not a comprehensive account of the whole. Inflation was proposed to solve a puzzle.
It solved the puzzle, and in doing so it created something harder to sit with than a puzzle. It created a context in which our cosmos is almost certainly a footnote, a rounding error. Something smaller than an atom in a universe too large to have a name. Cosmology has done this before. Copernicus moved Earth away from the center of the solar system. Then we learned the solar system was not the center of the galaxy. Then we learned the galaxy was one of hundreds of billions. Each time, the boundary of the known expanded, and our position within it shrank. Inflation is the latest and most violent of these contractions of significance. And unlike Copernicus, there is no new center waiting to be found.
There is just more.
Once you accept that inflation created a universe far larger than the observable part, a deeper question surfaces. Is that larger universe more of the same? Or is it something stranger? The physicist Max Tegmark has spent decades mapping out the logical possibilities. He describes 4 distinct levels of what we might call a multiverse. 4 tiers of strangeness, each one harder to grasp than the last. It is worth saying clearly from the beginning, some of these are rooted in mainstream physics. Others are speculative in ways that push against the limits of what we call science. But all of them follow from questions that the data already forces us to ask. The first level is the least exotic, almost deceptively simple.
If the universe is large enough, not infinite, just large enough, then by pure statistical necessity, every possible arrangement of matter must eventually repeat. There are only a finite number of ways to arrange particles within a region the size of our observable universe. The number is staggeringly large, roughly 10 to the power of 10 to the power of 122, but it is finite. A universe large enough to contain more than that many observable universe-sized regions must, somewhere, repeat.
somewhere at an unimaginable distance, further than any signal could ever travel, further than any spaceship could ever reach, further than any light could ever carry. There is a region of space with the same physical laws as ours.
The same constants, the same forces, and in that region, the same patterns will eventually emerge. The same distribution of galaxies, the same rocky planet at the right distance from the right kind of star, the same atmosphere, the same first cell, the same improbable chain of accidents leading to something capable of looking up and wondering. Possibly, and this is the part that resists comfortable processing, the same person, not a copy, not a simulation. The same arrangement of atoms in the same configuration, expressing the same thoughts, inhabiting what feels to itself like the same unique life. This is not philosophy. It is combinatorics. If space is large enough, you are not unique. You repeat.
Every version of you that could exist, every decision ever made differently, every moment of luck that went another way, exists somewhere in the Level 1 multiverse. Not as a possibility, as an actuality. Sit with that for a moment. The second level is harder. This is where Goethe's inflation becomes stranger still. In 1983, the physicist Andre Linde proposed a modification to inflation called eternal inflation. In the standard picture, inflation switches off everywhere and the universe cools into the hot, dense state we call the Big Bang. But Linde suggested that inflation might not end everywhere at once. In some regions of space, quantum fluctuations might cause inflation to stop, and those regions would cool and expand into pocket universes like ours.
But in the surrounding space, inflation would continue, roaring outward, never stopping. From that still inflating background, new bubbles would constantly nucleate. New pocket universes, each one expanding from within, while the space between them continues to inflate. Each bubble universe would be causally disconnected from every other, moving apart at rates that make them permanently inaccessible to one another. An ocean of expanding space, populated by an infinite family of isolated bubble universes, each one a cosmos unto itself. This is eternal inflation, and it produces not one large universe, but something closer to an infinite ensemble of separate cosmoses, each sealed off from the rest by the relentless expansion between them. But here is what makes the Level 2.
In eternal inflation, different bubble universes may not share the same physical constants. The strength of gravity, the mass of the electron, the cosmological constant itself, the very dark energy we were tracing in the last chapter. In the theory of eternal inflation combined with string theory, there may be an enormous landscape of possible values for these constants. Estimates suggest something like 10 to the power of 500 different possible configurations. Each bubble universe might freeze with different values, different physics, different chemistry. Perhaps no chemistry at all. In some bubbles, the cosmological constant might be so large that the universe tears itself apart before any structure can form. In others, it might be so negative that the universe collapses in seconds.
In some, the electromagnetic force might be too strong for atoms to hold together. In others, the nuclear force might be too weak for stars to ignite.
Most bubble universes, by this logic, would be empty of complexity, sterile, dark, uniform. Only in the rare bubbles where the constants fall within a narrow range, just strong enough, just weak enough, just constant enough, would anything interesting emerge. Galaxies, stars, elements, life. This is speculative. We have no direct evidence for other bubble universes. We may never have direct evidence. They are, by construction, beyond our event horizon. But eternal inflation follows naturally from the inflationary models that are our best current explanation for the CMB. The two ideas are connected.
To accept inflation is to at least take eternal inflation seriously as a possibility. The third level comes not from cosmology, but from quantum mechanics, and it requires setting aside a different kind of assumption. In 1957, a physics graduate student named Hugh Everett proposed a radical interpretation of quantum theory. At the time, the standard view was that quantum systems exist in superpositions of multiple states, a particle spinning both up and down, a radioactive atom both decayed and intact, until a measurement is made, at which point the wave function collapses into one definite outcome. But Everett asked a question no one had asked in quite that way before. What if the wave function never collapses? What if all the possible outcomes always occur?
What if when a quantum event happens, the universe branches, splitting into multiple copies, each one realizing a different outcome? In this interpretation, the many worlds interpretation, there is no random collapse. There is only branching. Every quantum event since the beginning of time has produced a branching of reality. Every radioactive decay that might or might not have happened, every photon that might or might not have scattered, every quantum process in every atom, in every star, across the entire history of the cosmos, each one produced a fork. By now, the number of branches is a number that cannot be written down. It is larger than any quantity that has ever been assigned a name. In one branch, a particular star formed.
In another, it did not. In one branch, a particular molecule became the first self-replicating thing on a particular world. In another, it did not. In one branch, a particular nerve fired in a particular brain, and a decision was made. In another, the nerve did not fire, and the decision went differently. Every road not taken, every coin that landed the other way, every accident that did not happen. The many worlds interpretation is not universally accepted. Physicists disagree about whether it is the most coherent way to interpret quantum mechanics, but it is taken seriously, genuinely seriously, by serious physicists. It resolves certain paradoxes in quantum theory in ways that other interpretations struggle with.
It does not introduce arbitrary rules about what counts as a measurement, or when exactly a wave function should collapse. It simply says, all outcomes occur, always. And then there is the fourth level, the most speculative, the hardest to even articulate without feeling that language itself is straining at its seams. Tegmark's own contribution to this taxonomy, the mathematical universe hypothesis, the idea that every mathematically consistent structure does not merely describe something that could exist, it actually exists. There is no distinction, at the deepest level, between mathematical possibility and physical reality. Our universe is one mathematical structure among all possible mathematical structures, and each of them is equally real, equally instantiated, equally there. What does this mean? It means that if a universe can be described by a consistent set of mathematical rules, it exists, not as an abstraction, not as a potential, as something actual. A cosmos with different numbers of spatial dimensions. A cosmos governed by different equations of motion. A cosmos so alien in its fundamental structure that we have no words for what it might be like, because our words grew from inside a cosmos with completely different rules. If the mathematical universe hypothesis is correct, then the question, why is there something rather than nothing, dissolves entirely. There is no nothing. There is every possible something, all of them equally real, equally present, equally ongoing.
And we inhabit one of them. The one whose mathematical structure happens to permit atoms and stars and observers capable of asking why. This is deeply speculative. It cannot be tested in any conventional sense. It is a philosophical position dressed in mathematical clothing, or depending on how you look at it, the most radical possible extension of what taking mathematics seriously implies about the nature of existence. What do we do with all of this? We cannot test most of it. The other bubble universes, by construction, are beyond any possible observation. The other branches of the quantum wave function do not interact with ours in ways we could detect. The other mathematical structures, if they exist, are sealed away by definition.
These are frameworks that float at the edge of science. Genuine theories with genuine internal logic proposed by genuine scientists, but untethered from the anchor of experimental confirmation. There is something uncomfortable about that. Science depends on falsifiability. A claim that cannot be tested even in principle is not science in the traditional sense. And yet, the multiverse is not a mystical claim. It is a consequence. It follows from equations that were written to explain things we actually observe. The discomfort is not that the multiverse is unscientific. The discomfort is that science, taken seriously enough, leads to conclusions that lie beyond the reach of science. That is a strange place to find yourself. And perhaps the strange place is itself the answer.
Perhaps the universe is not built to be fully comprehensible to the things it produces. Perhaps the boundary of knowledge is not an accident of our current tools or our current intelligence. Perhaps it is a structural feature, a hard limit built into the geometry of information and causality that no amount of cleverness will overcome. We know enough to suspect that universe, the word that once meant everything that exists, almost certainly refers to something far smaller than what exists. We have expanded the meaning of that word with each passing century. And each expansion has revealed not a final answer, but another question larger than the one before it.
There is something else pressing outward, something we cannot see, cannot touch, cannot collect in any instrument. Something that makes up roughly 68% of the total energy content of the universe, and whose nature remains one of the deepest unsolved problems in all of physics. We call it dark energy. The story of its discovery begins in the late 1990s. 3 independent teams of astronomers, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the others led by Brian Schmidt and Adam Rees, were studying a particular kind of stellar explosion called a Type Ia supernova. These explosions are cosmologically useful because they are, to a good approximation, standard candles. They always reach approximately the same intrinsic brightness when they peak.
By measuring how bright a supernova appears and comparing that to how bright it actually is, you can calculate how far away it is with precision. And by measuring how much the light from that supernova has been stretched by the expansion of the universe, the cosmological redshift, you can reconstruct what the universe was doing at the moment the light was emitted. The expectation in 1998 was that the expansion would be slowing down. The universe is full of matter. Matter has gravity. Gravity pulls things together. The expansion of the Big Bang, everyone assumed, was gradually being reined in by the collective gravitational attraction of everything in the cosmos.
The only question was whether the universe would eventually stop expanding and collapse back in a big crunch, or whether it would expand forever but more and more slowly. What they found broke the model entirely. The distant supernova were too dim. Not by a little, by a measurable, systematic amount. They were farther away than they should have been if the expansion of the universe were slowing down. The only explanation was that the expansion was speeding up. Something was pushing outward. Something was overcoming gravity on the largest scales. Something was making the universe expand faster and faster with each passing billion years. Both teams, working independently, reached the same conclusion. The universe is accelerating.
This discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011, and it forced a rewrite of cosmology that the field is still absorbing. The leading explanation for this acceleration is the cosmological constant, a term that Albert Einstein originally introduced into his equations of general relativity as a mathematical fix. When Einstein first wrote down his field equations in 1915, they described a dynamic universe, one that had to be expanding or contracting. Einstein found this troubling. The universe, he believed, was static and eternal. So he added a term to the equations, a constant denoted by the Greek letter lambda, that provided a counterbalancing outward pressure, holding the universe steady.
When Hubble proved in 1929 that the universe was expanding, Einstein abandoned the cosmological constant, reportedly calling it his greatest mistake. For decades, lambda sat in the dustbin of physics, an embarrassing historical artifact. And then in 1998, it came back. If the cosmological constant is real, if it represents an intrinsic energy density of empty space, a quantum property of the vacuum itself that does not dilute as the universe expands, then it provides a natural explanation for the observed acceleration. As the universe grows larger, ordinary matter and dark matter become more spread out, their density falling. But the cosmological constant's density stays fixed. It is a property of space, not of the stuff in space.
So as space expands, the cosmological constant's contribution grows relative to everything else. Eventually, it dominates. And when it dominates, it drives acceleration. This is the mainstream scenario. This is what current observations are most consistent with. If the cosmological constant holds, the fate of the universe is something physicists call the Big Freeze, or sometimes, more poetically, heat death. Galaxies beyond our local group will drift past our event horizon, one by one, until the observable universe contains only the local group. Stars will continue to form for another trillion years or so, fueled by the remaining clouds of gas. But the gas will gradually be depleted. One by one, the stars will burn out.
Stellar remnants, white dwarfs,
neutron stars, black holes, will persist for vast spans of time. But eventually, even black holes will evaporate, radiating their mass away as Hawking radiation over timescales so long they make the current age of the universe look like a single clock tick. What remains will be a universe of almost perfect emptiness. A cold, dark, nearly featureless expanse, populated by the last cold embers of matter, separated by distances growing larger with every passing moment, with no energy gradient left to drive any process, any chemistry, any event. Not an explosion, not a collapse, just silence, growing colder and more absolute forever. But there is a darker possibility.
In 2003, physicist Robert Caldwell proposed a hypothetical form of dark energy called phantom energy. Most forms of energy and matter have what is called a positive equation of state. They behave in ways that intuitively make sense. Their density either stays constant as the universe expands, or it decreases. Phantom energy is different. Its density increases as the universe expands. The more space there is, the more phantom energy there is in that space. This violates what physicists call the null energy condition, a basic assumption built into most cosmological models. If phantom energy exists, the consequences are catastrophic in a literal sense. The acceleration of expansion would not merely continue, it would intensify. The rate of growth would itself grow.
The universe would expand faster and faster with each passing moment, and the distance between objects would increase without limit on timescales shorter and shorter than the one before. Caldwell called this the Big Rip, and it works approximately like this. In the early stages, galaxy clusters, bound together by gravity across millions of light years, would be torn apart as the expansion between their members outpaced the gravitational attraction holding them together. Then individual galaxies would come apart, then solar systems. Then, as the expansion became strong enough to overcome the forces governing smaller scales, planets would disintegrate. Oceans would be ripped apart. Molecules would be pulled apart at the covalent bonds. Atoms themselves, held together by the electromagnetic force, would be sundered.
And in the final fractions of a second before the singularity, the strong nuclear force binding protons and neutrons would give way, and the hadrons themselves would dissolve. The Big Rip, by some estimates, would occur approximately 20 billion years from now. Not an imminent threat, but finite, a definite ending. Is it real? Current observations are most consistent with the cosmological constant, dark energy that neither increases nor decreases over time. But the measurements are not precise enough to rule out phantom energy. The difference between the two scenarios in current data is smaller than our error bars.
We are, in this sense, genuinely uncertain about whether we live in a universe headed for cold, eternal silence, or one headed for a violent tearing apart of all structure at a fixed date in the future. We do not know which kind of universe we are in. We are passengers in a vessel whose engines we cannot fully inspect, traveling toward a destination we cannot see at a speed that is increasing. We know we are accelerating. We can measure the acceleration. We cannot determine whether the acceleration is constant or growing. And the difference between those two answers is the difference between two entirely different endings. What is most extraordinary is not the uncertainty about our fate. It is that we detected dark energy at all.
We built civilizations. We charted every star visible to the naked eye.
We developed calculus and general relativity and quantum field theory. We sent probes to the edges of the solar system. We mapped the three-dimensional distribution of galaxies across billions of light years. And through all of it, we were embedded in something that constitutes 68% of the universe's total energy content. And we had absolutely no idea it was there. It did not announce itself. It left no obvious signature in any individual observation. It revealed itself only through the systematic comparison of the apparent brightness of distant stellar explosions. A difference so subtle that most scientists, when first confronted with the data, looked for the mistake before accepting the result.
The universe kept its largest secret from us for 13.5 billion years. And then it whispered it, barely, through the faintness of a few hundred supernovae. What else might be there, pressing on the structure of reality in ways we cannot yet feel? There is a number that physicists sometimes describe as the worst prediction in the history of science. Quantum field theory, our most precisely tested theory of how particles and forces behave, predicts a value for the energy density of the vacuum. That is, the energy of empty space. This is the quantity that, in the form of the cosmological constant, drives the acceleration we just described. The observed value of the cosmological constant is extremely small. Not zero, but almost.
Just large enough to drive the acceleration we measure. Small enough that it did not overpower gravity and prevent galaxies from forming. The theoretical prediction from quantum field theory is different from the observed value by a factor of 10 to the power of 120. That is not a rounding error. That is the largest discrepancy between a theoretical prediction and an observation in the history of quantitative science. We do not understand why the cosmological constant has the value it has. We do not understand why it is not zero. We do not understand why it is not so large that the universe tore itself apart before any structure could form.
It sits at this particular value, small enough for galaxies, large enough to drive acceleration. And we have no deep explanation for why. Some physicists invoke the anthropic principle. Perhaps the cosmological constant has this value because only universes with this value permit observers to exist. In a vast ensemble of universes, each with different values of the cosmological constant, we necessarily find ourselves in one that permits our existence. We could not observe a universe in which no observers exist. This reasoning is logically valid. It is also deeply unsatisfying. It explains nothing about the underlying mechanism. It simply reframes the question, and whether it constitutes a scientific explanation or an abdication of explanation is a matter of genuine, ongoing debate among serious physicists.
We accelerate through space in a universe whose most dominant constituent we cannot explain, not in the sense of lacking data, but in the sense of lacking any framework that connects the observation to a deeper principle. Dark energy is real. Its effects are measured to high precision, and it remains, at its root, a mystery.
There is a particular kind of grief in this. Not the grief of losing something that was taken, not the sharp grief of destruction, but the quiet grief of watching something drift away. Slowly, irreversibly, without any dramatic ending,
until it passes beyond a line from which it will never return. Tonight, the observable universe contains something in the region of 2 trillion galaxies. 2 trillion. Each one a vast collection of gas and dust and ancient starlight and remnant stellar corpses, and perhaps, somewhere in the vast statistical ensemble of it all, something looking back. 2 trillion separate cosmoses in miniature, each one burning across hundreds of billions of years, with light that has been traveling toward us for longer than the Earth.
But that number will not hold. The expansion of the universe is not uniform in its consequences on small scales. The scale of galaxies, of galaxy clusters, of the groups of clusters called superclusters. Gravity is strong enough to hold things together. The Milky Way is not being pulled apart by the expansion of space. Neither is the Andromeda Galaxy, our nearest large neighbor. In fact, Andromeda is approaching us. It will collide with the Milky Way in approximately 4.5 billion years. Gravity wins locally. But beyond a certain distance, beyond the scale of the local group and its immediate gravitational neighborhood,
and those clusters are moving away from us at speeds that only increase with time. There is a boundary, our cosmic event horizon, beyond which no light emitted today will ever reach us. Not because of the speed of light, but because the space between us and those regions is expanding faster than light can traverse it. The expansion does not violate relativity. Light travels at light speed through local space. But when local space itself is expanding, the effective speed at which distant objects recede from us can exceed the speed of light. And for regions beyond the event horizon, the recessional speed is such that no signal emitted now will ever close the gap.
Any galaxy currently beyond our event horizon has already sent us its last message. Not its last message of this century, its last message ever. Astronomers have modeled what the observable universe will look like in 150 billion years. The calculation is straightforward once you know the expansion rate and the cosmological constant. By then, virtually every galaxy we can currently observe will have receded past our event horizon. The light from those galaxies, still traveling, still crossing space, will be so red-shifted by the expansion that it will be undetectable. Its energy diluted across wavelengths too long for any instrument to gather. The galaxies will not be destroyed. They will not cease to exist. They will simply be gone from our sky. Permanently. Irreversibly.
Without ceremony. The only galaxies remaining within our observable universe will be the approximately 50 members of the local group, our gravitational family. The Milky Way and Andromeda, by then, long since merged into a single elliptical galaxy, and the assorted dwarf galaxies bound to them. Everything else, the Virgo cluster, the Coma cluster, the Perseus cluster, the Great Wall, every structure visible in the deepest images our telescopes have ever captured, all of it will have passed beyond the edge of the knowable, and the evidence will not linger.
A civilization living on a world in that far future. If such a thing is possible, if intelligence persists across that span of time, we'll look out at the night sky and see something profoundly different from what we see. They will see the merged remnant of their galaxy. They will see, perhaps, a few nearby dwarf companions, and beyond that, darkness, black sky, no distant smears of light at the limits of their instruments, no red-shifted signals from remote clusters, no cosmic microwave background. By then, the CMB will have cooled to wavelengths so long that it will be indistinguishable from the noise of the quantum vacuum. That future civilization, if it is curious, will not know what it is missing. They will measure their galaxy.
They will map its stars. They will find no evidence of any cosmic expansion, because there will be no other galaxies close enough to show a redshift. The equations of general relativity will give them a static-looking cosmos. The cosmological constant will look from their vantage like a minor correction term with no particular significance. They will have no way to know that space itself was once expanding. They will have no way to know that the universe was ever larger than what they can observe. They might conclude perfectly reasonably that the cosmos is a single galaxy surrounded by eternal void. They will be wrong, but they will have no way to know it, and no evidence will survive to correct them.
We happen to live in an unusual moment. We exist in a window of cosmic time that is, in retrospect, extraordinarily favorable for knowledge. The universe is old enough that structures have formed. Galaxies and stars and planets and the long, slow chemistry of life. But it is not yet so old that the expansion has swept everything away. We live in the era when both the relics of the beginning and the full population of the observable universe are simultaneously accessible. The cosmic microwave background, that faint glow from 380,000 years after the Big Bang, when the universe first became transparent, is still detectable, still measurable.
Still carrying in its pattern of temperature variations the seeds of every structure that would ever form. In a few 100 billion years, it will be gone, redshifted to energies too low to measure against the background noise. The distant quasars and galaxies whose light has been traveling for 12 and 13 billion years are still, barely, within reach of our instruments. In a few billion years, the most distant of them will have crossed our event horizon and vanished. In 100 billion years, almost all of them will be gone. The evidence that allowed us to discover dark energy, the systematic dimming of distant supernovae, required galaxies far enough away to show a meaningful redshift, and bright enough to be detected across those distances.
That window of observational accessibility will close. The measurements we have made, the conclusions we have drawn, the cosmological model we have assembled, these required being here now, in this era, in this window. We are fortunate, not in the sentimental sense, in the strictly mathematical sense. The probability of being born in the era when the cosmos is most legible, when the most evidence is available, is not guaranteed. We happen to be here, and that means we happen to know things that will be unknowable forever after. But the knowing is not without its weight, because we know, now, that the window is closing, that each year that passes, the accessible universe shrinks a little. Each year, the expansion carries a few more galaxies past the boundary of our event horizon. Not dramatically, not all at once,
quietly. One galaxy, or one cluster, or one filament of the cosmic web, easing past the edge and disappearing without any sound, without any signature, without any record of its departure. Somewhere out there right now, there is a galaxy whose last photon capable of reaching us is already in transit, already crossing billions of light years of expanding space, stretched thinner with every second, racing a horizon that it will just barely beat or just barely lose. If it loses, we will never know that galaxy existed. It will simply never appear in any observation. There will be no gap in the data.
No absence where a presence should have been, just nothing. If it wins, the photon will eventually be collected by some detector, perhaps a telescope not yet built, perhaps a civilization not yet born, and contribute a single count to a survey of the sky. And in the next epoch, there will be no more photons from that galaxy. The source will fall silent, not because it died, because the space between us grew. The loss happens without drama. The universe does not mark it. There is no signal, no alarm, no record of what passed beyond. Things simply cross the line and are gone. And the universe continues, indifferent, expanding at its measured rate, carrying everything outward with it.
There is one more thing to say about this. When we look at the night sky, when we see the faint smudge of a distant galaxy in a long exposure photograph, we are not seeing it as it is. We are seeing it as it was, when the light we are now collecting left it. We are looking at the past always. The further away a galaxy is, the further back in time we see it. Some of the galaxies we observe no longer exist in the form we see them. They have evolved. They have merged with neighbors. Their stars have aged. Perhaps their stellar populations are entirely different from the ones whose light is currently reaching us.
We see them as they were, and we know dimly that what we are actually seeing is a ghost, an echo, a message from a past that no longer exists in quite that form. And some of those galaxies, the ones closest to our event horizon, will send us no more messages. What we have already received is all we will ever get. The last photon has already left. It is already on its way. And when it arrives, that chapter of information will close. We will not notice. We do not have instruments sensitive enough to catch the final transmission. It will simply be one data point among billions. And then, in the next survey, one fewer point than before. The loss will be silent.
And it will be permanent. This is not a problem with a solution. No telescope, however large, can gather light that never arrives. No spacecraft can reach a galaxy receding faster than the speed of light. No civilization, however advanced, can communicate across a causal barrier that the geometry of expanding spacetime makes absolute. The loss is written into the structure of the cosmos. It is built into the equations alongside the gravitational constant and the charge of the proton. It is not an accident. It is not a technical limitation. It is a feature of the universe itself. The universe contracting what is knowable, slowly, irreversibly, across all of time. And we are the only things we know of who are aware of this.
Who can trace the geometry of the loss? Who can feel something? Call it what you will. When they understand that the universe is becoming less legible, not more, as time goes on. whether that awareness matters, whether it changes anything about the geometry of what is being lost, is a question the universe will not answer. The galaxies drift, the horizon tightens, the sky grows a little darker, a little quieter, a little more alone, and the expansion continues, measured and indifferent, carrying everything outward. Everything beyond our reach will keep receding, and one day, even the memory of their existence will be gone.
Everything beyond our reach will keep receding, and one day, even the memory of their existence will be gone. But before we arrive at that final silence, there is a question that has lived at the center of physics for decades. A question so uncomfortable that some physicists have stopped trying to answer it directly, and have chosen instead to live with the unease it creates. It begins with empty space. Not the empty space between galaxies, or the thin vacuum between atoms. Something deeper. Quantum field theory, the most precisely tested framework in all of science, tells us that empty space is not truly empty. At the smallest possible scales, fields flicker. Particles arise and disappear. The vacuum itself has energy.
It has measurable consequences. The Casimir effect, the faint attraction between two uncharged metal plates held close together in a vacuum, exists precisely because of this flickering. The energy of nothing, pressing in from the sides. So quantum field theory predicts a value for the energy density of empty space. A number. A specific, calculable number based on the behavior of fields at the smallest scales we can probe. That number is wrong by a factor of 10 to the power of 120. Let that settle for a moment. 10 to the 120th power. That is not a rounding error. It is not a small correction waiting to be made.
It is the largest discrepancy between theoretical prediction and physical observation in the entire history of science, by a margin that is itself almost incomprehensible. The energy density we actually observe, the dark energy that is driving the expansion of the universe, is almost exactly zero compared to what the equations say it should be. Not precisely zero, but absurdly, suspiciously close to zero. Close enough that galaxies can form, close enough that stars can burn, close enough that something as fragile and temporary as a conscious mind can arise. If the vacuum energy were even a few orders of magnitude larger than it is, the universe would have expanded so fast after the Big Bang that no structure would ever have formed.
No clouds of gas, no stars, no planets, no chemistry, no time for anything to develop. If it were slightly negative, the universe might have collapsed back in on itself long before now. The number we observe is the number that allows us to exist, and we have no idea why. This is what physicists call the cosmological constant problem, and it has two deeply unsatisfying possible answers. The first is that there is some cancellation mechanism we do not yet understand. Some symmetry, some as yet undiscovered physics, that takes the enormous vacuum energy predicted by quantum field theory and scrubs it down to nearly nothing. Many have searched for this mechanism. None have found it, The second answer is the anthropic argument.
The idea that the cosmological constant has the value it has because if it were different, we would not be here to ask the question. That in a vast landscape of possible universes, each with its own vacuum energy, we find ourselves in one of the rare pockets where the number is compatible with life. This answer troubles many physicists. It feels like explaining a mystery by pointing to our own existence. And yet, it has proven stubbornly difficult to rule out. Consider what this implies. Not just that we are small, not just that we are brief,
but that the very laws underpinning the universe we inhabit, the invisible numbers specifying how empty space behaves, may have no deeper explanation than the fact that we are here, asking about them. The universe did not have to be this way. Or rather, among all the ways it could have been, this is one of the extraordinarily rare configurations in which minds emerge to wonder at the configuration. We are not at the center of space. We are not at the center of time. But we may be, in some strange and accidental sense, at the center of possibility. In a universe that is just barely gentle enough to permit us.
And we do not know if that is a profound discovery or simply the echo of our own existence, bouncing back at us from the walls of the universe.
There is an older question, one that began much smaller. Stephen Hawking showed in the 1970s that black holes are not entirely black. They radiate, slowly, imperceptibly, over timescales that dwarf the current age of the universe. Black holes leak energy. They evaporate, and eventually, after a time that makes the current age of the cosmos look like a single heartbeat, a black hole disappears entirely. What happens to everything that fell in? This is the black hole information paradox. Information in physics is not just data. It is the complete description of a physical system. Every particle, every spin, every quantum state. The laws of quantum mechanics say that information cannot be destroyed. It can be scrambled, hidden, transformed.
But the underlying description of a system must survive in some form, somewhere. But if a black hole evaporates completely, and the radiation it emits carries no record of what fell in, then information has been destroyed. Quantum mechanics would be broken, at least in that regime. This contradiction has occupied some of the sharpest minds in physics for half a century. One proposed resolution comes from the holographic principle, first articulated by Gerard 't Hooft and later developed by Leonard Susskind. It suggests something strange and beautiful, that all the information describing a volume of space can be encoded on its boundary, the way a three-dimensional image can be stored on a flat surface.
The interior of a black hole, in this view, is not truly separate from its surface. Information falls inward, but a complete description is retained at the event horizon, encoded in a form we do not yet understand. The information is not lost. It is translated. Now expand this idea to the scale of the universe itself. The cosmological event horizon, the boundary beyond which nothing can ever reach us, is not just an edge of observation. It is, in some theories, a physical surface. And the holographic principle applied at this scale suggests something extraordinary, that all the information within our observable universe may be encoded on that distant boundary.
That the three-dimensional world we inhabit, every particle, every field, every thought, might be, in some sense,
a projection from a two-dimensional surface at the edge of everything we can see. This is not science fiction. It is a serious hypothesis in theoretical physics, arising from string theory and the study of quantum gravity. The correspondence between surfaces and volumes, between boundaries and interiors, has been demonstrated rigorously in certain mathematical frameworks. But what does it mean for the galaxies we are losing? Right now, there are galaxies crossing our event horizon, receding beyond the boundary from which no signal will ever reach us. In the ordinary sense, they are gone. Their light will never arrive. No probe we could send would ever reach them.
They have passed into a region causally disconnected from everything we will ever experience. But if the holographic principle holds, the information describing those galaxies, every star, every world, every particle, is not erased. It is encoded somewhere on the surface of our cosmological horizon, like a shadow pressed into the boundary of our universe. They exist in some encoded form at the very edge of what we can call our universe. Not gone, translated. There is something quietly strange about this picture. We think of an edge as a place where things end, where structure gives way to nothing. But the holographic principle suggests that edges are not endings. They are archives.
The most distant boundary of our observable universe may be the most information-dense surface in existence. Everything that has ever crossed into the dark is written there, in a language we cannot read, in a script we have not yet learned to see. The universe does not discard what it can no longer see. It keeps a record pressed flat against its own horizon, patient and unreadable, for however long the horizon stands. Whether that record matters, whether there is any sense in which it constitutes existence, is a question that physics has not answered. Perhaps it cannot. Perhaps the distinction between existing somewhere we cannot see and not existing at all is itself a question our language is not equipped to ask.
We built our words for a world where the things we cannot see are still, in principle, reachable, where the horizon is a limit of vision, not a limit of being. The cosmological event horizon is something different. It is a limit of causality. Beyond it, not just sight, but influence, fails entirely. And yet the equations do not give us nothing. They give us something we cannot interpret, a description encoded in a surface of a reality we can never visit.
There is a particular kind of limitation that is harder to sit with than ordinary ignorance. If you do not know the answer to a question, you can at least form the question. You can picture the shape of the gap in your knowledge. You know that you are missing something, and you can gesture at what kind of something it might be. But there is a deeper form of not knowing, one where the question itself cannot quite be formed, where the concepts required to even ask the question are ones your mind does not have. Consider the dimension of time. You have always experienced it in one direction, forward. The past is fixed and unreachable. The future is open but unknown.
Every framework of thought you possess assumes this structure. Cause before effect, memory of the past, not the future. The entire architecture of human consciousness is built on the assumption that time flows in a single direction. But the fundamental equations of physics are almost entirely time-symmetric. They work equally well run forward or backward. The arrow of time, the felt, lived sense that there is a before and an after, is not built into the deepest laws we know. It emerges from statistical behavior, from entropy, from the particular low entropy state the universe happened to begin in. Most people, when they hear this, can engage with it intellectually. They can follow the argument.
But they cannot feel what it would be like for time not to have a direction. The intellectual understanding floats above something the mind refuses to actually inhabit. Now imagine trying to think about what lies beyond the cosmological event horizon, not just the scale problem, though that is real. Human intuition for distance fails well before we reach even the nearest star. Beyond the observable universe, on scales 10 to the 23rd times larger than what we can see, intuition simply does not operate. The numbers exist on paper. They do not exist anywhere in the mind. The deeper problem is conceptual. The observable universe is a region defined by the reach of light and causality from where we stand.
Everything within it shares a common past, a common origin, a common set of physical laws that have been tested and refined over decades of observation. When we talk about the universe beyond our horizon, we are extrapolating those laws into a region we can never probe. And the extrapolation may fail. Inflationary cosmology, our best current framework for what happened in the first moments after the Big Bang, does not predict a universe beyond the horizon that is simply more of the same. It predicts a universe in which the conditions of inflation did not end everywhere at once, in which different regions nucleated out of the inflationary field at different times.
In which the physical constants, the number of large dimensions, the very structure of quantum fields might be different. A region of the universe where space has 4 large spatial dimensions instead of 3 would not just look different. It would be governed by different equations. Gravity would fall off as the inverse cube of distance instead of the inverse square. Stable orbits would be impossible. The complex chemistry that enables stars and planets would not arise. A mind that evolved in such a region, if minds could evolve there at all, would have no intuition for 3-dimensional space, would not understand, at a felt level, the geometry we take for granted. What would such a mind make of our universe?
What concepts would it reach for that we do not have? What questions would it think to ask that we have never thought to formulate? We cannot know, not because we lack the data, though we do, but because we lack the cognitive architecture. The philosopher Thomas Nagel wrote about what it is like to be a bat. Bats experience the world through echolocation, through a rich spatial map built from sound reflections. We can describe this scientifically. We can understand it intellectually. But we cannot know what it is like from the inside. The felt, first-person experience of navigating space through reflected pulses of sound is inaccessible to a creature that has never had it. The universe beyond our horizon is not a bat.
It may not even be a universe in any sense we would recognize. It may be a region in which the concepts of space and time, as we understand them, are not the right framework, where the questions we would naturally ask, how large is it? How old is it? What exists in it? Do not have well-formed answers because the concepts underlying the questions do not apply. This is what it means to encounter a genuine boundary of understanding, not a frontier where better instruments would help, not a gap where a smarter theory might reach, but a place where the very machinery of thought, the categories, the intuitions, the implicit assumptions built into language, begins to come apart. The ancient maps used to mark unknown territories with the phrase, "Here be dragons." The phrase was not really about dragons. It was about the failure of the map, the edge of the known, past which the cartography simply stopped working. The cosmological event horizon is that edge, but it is not just geographic. It is conceptual. It is the boundary past which our maps of reality, our equations, our intuitions, our language, may no longer apply. And unlike the ancient cartographers, we cannot simply sail out to find what is there. The deepest mystery is not what we do not know. The deepest mystery is that we cannot be sure what kind of thing we do not know.
Whether the gap is a scientific gap, waiting for a theory and a measurement, or something more fundamental, a gap in the very structure of thought, we are creatures shaped by 4 billion years of evolution on a single warm world. Our minds were built to navigate grasslands and social hierarchies, to track prey and recognize faces. The fact that this same mind can reach out and map the structure of space-time, can discover the rules governing particles smaller than any atom, can hold in abstract thought a universe 13.8 billion years old. This is extraordinary, almost unbelievable. But it would be equally extraordinary if a mind assembled for such modest purposes happened to be adequate to every question the universe contains.
Some truths may be too large for us, not too complex. Complexity is something minds can work through, slowly, with effort and time, but too structurally alien, requiring a kind of cognition that biological evolution on a small warm planet did not have occasion to develop. We are here at the edge of everything we can see, looking outward. And what we see at the farthest extent of our instruments and our mathematics is not an answer. It is the limit of the question.
Tonight, while you are still, the universe is moving. Every second that passes, the fabric of space stretches a little further. The galaxies at the edge of our observable universe recede a little faster. Some of them, the ones already near our cosmological horizon, step across it, silently and permanently. Their last light, already traveling toward us, will arrive in billions of years. After that, nothing. No signal. No trace. Not even the faint microwave glow of their ancient warmth. There is a future version of this universe that is very quiet. Not immediately. There are billions of years of ordinary time ahead. Stars still forming, still burning, still dying in slow collapse or brief, brilliant explosion.
The Milky Way and Andromeda will collide in roughly 4 billion years, not in catastrophe, but in slow gravitational embrace, the two becoming one vast elliptical galaxy, most of their stars never even coming close to another. For a long time after that, there will still be stars, but they will burn through their fuel, the most massive ones first, in millions of years. Then, the sun-like stars in billions, then the small, cool red dwarfs in trillions. One by one, the lights go out, not together, not in a single dramatic moment. Just one by one, across an unimaginable span of time, each star exhausting the last of its hydrogen, collapsing into a cooling remnant, fading to nothing.
Eventually, the only light sources will be white dwarfs, the dense, cooling embers of dead stars,
slowly radiating their remaining heat into a universe that has grown too large and too cold for the heat to matter. This is what physicists call the heat death. Not a violent end, not an explosion or a collapse. Just the final, quiet equalization of temperature across a universe that has grown so large and so empty that no gradient of energy remains. No difference in temperature means no possibility of work. No work means no process, no change, no event. Time would still pass, but nothing would happen. And somewhere in this long dimming, a strange thing will have occurred.
The descendants of intelligent life, if any persist that far, will look out at the sky and see almost nothing. The other galaxies, the trillions of galaxies visible to us today, will have long since crossed the event horizon. Their light will have stopped arriving so long ago that no memory of their existence will remain. No fossil record in the physics of the universe. No echo. The cosmic microwave background, the faint afterglow of the Big Bang, the oldest light we can detect, the wall that defines the farthest edge of our observable universe, will have been stretched by the expansion of space until its wavelength is longer than the observable universe itself. It will have become, for all practical purposes, undetectable.
A cosmologist in that era, living in the remnant of what was once the local group, surrounded by the cooling embers of dead stars, would look out at an empty sky and have no way of knowing the universe was ever different. No way of knowing that 100 trillion galaxies once blazed across a sky, that living things on a small, warm planet once stared up at, in wonder. They would have no evidence for the Big Bang, no cosmic microwave background to detect, no distant galaxies to map, no redshift data to reveal the expansion of space. Every tool of modern cosmology would be silent. Every measurement would return. Nothing.
They might develop theoretical frameworks, suggesting that the universe was once different, once younger, once smaller. But they would have no way to test it. The data that we take for granted, that our instruments gather every night, painting a detailed picture of the history and structure of the cosmos, would simply be gone, stretched beyond detection, receded beyond reach. We are living in a privileged moment, not privileged in any mystical sense, but privileged in the sense of timing. The universe is young enough that the light of the Big Bang still reaches us, old enough that galaxies and stars have had time to form.
And we happen to evolve during this narrow window, a window that, measured against the full span of cosmic time, is extraordinarily brief, in which the sky contains everything we need to figure out what the universe is. This is not cause for comfort. It is cause for a particular kind of awe that does not resolve into anything reassuring. We are not here at the beginning of the universe. We are not at the end. We are, in a deep and accidental sense, at the moment of maximum legibility. The universe, right now, is as readable as it will ever be. And we have the instruments and the mathematics to read it, barely, with tremendous effort, imperfectly. The window is open now. It has always been closing. You are lying here, in the dark. The Earth turns under you. The Milky Way arcs overhead, 100,000 light years of stars and gas and dust wheeling slowly in the dark. Beyond it, the local group, a few dozen galaxies bound to each other by gravity. Beyond that, the Virgo supercluster, then the Laniakea supercluster, then the great cosmic web of filaments and voids that stretches to the edge of what we can see. And beyond that, more, in all directions. Without end, or if there is an end, it is an end we can never reach, never see, never even define in any way we could agree on. The horizon moves with you. It always has.
Every point in the universe is the center of its own sphere of visibility, its own bubble of observable space. The light that has had time to reach this location, this tiny point in an incomprehensibly vast structure, defines your universe. Not the universe, your universe. And it is unique to this place and this moment. Every second it grows slightly larger as light from slightly farther away finally arrives. And every second it is also contracting in another sense, as galaxies near the edge recede past the point of return. You are at the center of a sphere that is always growing and always losing ground. The philosophers and the physicists and the mathematicians have been circling this territory for decades. What is the universe? How large is it?
Is it infinite? Does it have a shape? Are there others? What happened before it began? What lies outside it? These questions are not rhetorical. They are real questions with real attempts at answers. The answers are partial. They are strange. They require mathematics most people will never study, and even with that mathematics, they remain provisional, contested, unfinished. But beneath all of them, there is something simpler, a feeling that precedes the mathematics. The feeling you have when you lie in the dark and let your mind reach outward, past the ceiling, past the atmosphere, past the orbit of the moon and the edge of the solar system, past the nearby stars and the far arm of the galaxy, past the local cluster and the supercluster, past everything you have ever seen or could see, past the edge of what light has had time to carry, past the horizon, and realize there is still more. The universe does not stop at the edge of your seeing. It has never cared where your seeing stops. It continues, in whatever form it takes, with whatever physics it obeys, across whatever distances cannot be measured, in whatever dimensions cannot be visualized, completely indifferent to the boundary your biology has drawn around what you are able to know. There is something in this that is not frightening, exactly, or not only frightening. There is something in the sheer scale of the unknown that is, in a strange way, restful. You do not have to solve it. You could not solve it if you tried. No collaboration of every human mind that has ever existed, working for every year that remains before the stars go out, would close the gap. The horizon recedes faster than any mind can follow. The not knowing is not temporary. It is permanent.
It is structural. It is woven into the geometry of space and the finitude of light, and there is a kind of freedom in that. The ancient question, what is out there, has an answer that is not an answer. There is more. There is always more. More space, more structure, more history, more physics we have not guessed at, more forms of matter and energy, and possibly more forms of something we do not have a word for, extending in all directions without a discoverable limit. It was always this way.
It will always be this way. Every civilization that has ever looked up at the sky has looked up at the same irreducible mystery.
Every instrument ever built has pushed the horizon a little farther and found the same thing waiting: more horizon. This is not a failure of science. It is the shape of the territory. You are here, in this particular body, on this particular world, at this particular moment in the long history of a universe that did not need to produce you and does not particularly require your continued presence. The cosmological constant is set just barely low enough for galaxies to form. The stars burned long enough to forge the elements that make your body. The Earth is warm enough, and stable enough, and old enough for the chemistry of life to have had its chance. None of this was arranged for you. It was not arranged at all.
It simply is the way things are, in this corner of a vastness that extends beyond any horizon we will ever define. And somewhere out there, right now, galaxies are crossing the edge, silently, without drama, without any record being kept. One by one, they pass beyond the reach of any signal we might send, any light we might receive, any causal thread that could connect us. And the universe continues. Vast, indifferent, ongoing, holding more in every direction than we will ever be able to see. You are somewhere inside it. For now, beyond every horizon, there is more we will never